Hi, my name is Atsu, also known as Squid God, and today we'll be talking about performance for the Playdate. Optimizing for performance on the Playdate is unlike most other modern systems. This is because the Playdate's CPU, or central processing unit where all your code runs, is magnitude slower than not only something like your computer, but even just your phone. In addition, the Playdate has no graphics processing unit, or GPU, which is very rare for a modern device. Even the original Game Boy has a GPU in the form of its picture processing unit. Calculating and drawing things to the screen is a slow operation, and the burden is completely on the Playdate CPU to handle that, tightening your performance budget. Lastly, most Playdate games are written in Lua, which has a lot of easy pitfalls that you can fall into that can kill your performance. Of course, you can port some of your slow functions over to C, but in this video, I'll show you that it's probably not necessary. We'll go over how to find the performance bottlenecks in your games, along with several tips and tricks on how to maximize the performance of your game just using Lua. First, let's talk about what performance even is. On the Playdate, games run at 30 frames per second, or 30 FPS by default. That means that your game has 1/30th of a second, or about 33 milliseconds, to run all the code inside of your update loop, and also draw everything to the screen. Every line of code takes a certain amount of time to run, and when that time exceeds 1/30th of a second, the Playdate is forced to delay updating the screen to finish running your code. That's when your frame rate starts taking a hit and you get frame drops and lag spikes. Our goal with optimizing performance is to simply rewrite our code so that it always runs faster than 1/30th of a second every frame. Next, let's talk about why performance is important. The first reason is obvious. When your game starts to lag and drop frames, it's a frustrating experience for the player. Performance is something that players care about, and if it's bad enough, will poorly review a game for. In addition, I'd consider performance to be a feature in and of itself by enabling other features. Certain types of games that have a lot of elements moving on the screen is gated behind performance. You also need better performance if you want to run your game at a higher frame rate. For example, if you want to run your game at 50 FPS, you'll only have 1/50th of a second for each frame, which is 40% less time per frame than at 30 FPS. On top of that, the Playdate has a special consideration to make because of how Mirror works. Mirror is a companion application that lets you mirror your Playdate screen to the computer, which is great on its own, but especially as an accessibility feature because it allows you to see your game on a larger screen and use an alternative controller. However, the Playdate takes a huge performance hit because of the work required to send over the screen data every frame. In that sense, performance can potentially be an accessibility feature for the Playdate if your game can't run smoothly on Mirror. To begin, the most important part about optimizing your game performance is actually measuring the performance in the first place. Performance improvements are sometimes unpredictable, and you might make a big change that either does nothing or actually degrades your game performance, and we won't know unless we have some means to measure it. Now's probably a good time to point out that the simulator is not a good measure of performance on the Playdate. Since the simulator is running on your computer, it's running way faster than what your Playdate will run. The only way to get an accurate measure of the performance of your game is to upload your game to a physical Playdate device and test it there. The most straightforward way to gauge your game's performance is by simply getting the frame rate your game is running at. You can use the draw FPS function, which takes an X and Y coordinate to draw this little FPS box at. With this, you can just visually monitor your FPS to look for any frame drops. A good spot to draw it is just in the corner of the screen. Since the box has a width of 15 pixels and a height of 12 pixels, here are the X and Y coordinates if you want to draw the FPS at each of the different corners of the screen. Once the FPS counter starts dipping below 30, or whatever your target FPS is, then you know you have some sort of performance issue. If it's only dropping to 29 or 28 briefly, it's usually not a big deal, but if it's staying below or dropping further, then it's probably something worth addressing. You can also get the value directly using the getFPS function if you want to print the value, log an FPS history, draw it yourself with a different font, etc. A neat trick you can do to get a sense of how well your game is running is by uncapping your frame rate. The setRefreshRate function allows you to set a target refresh rate, which again is 30 by default. However, if you set it to 0, then it actually uncaps the frame rate. This means that the Playdate will draw to the screen as soon as all your code is finished running each frame, which will make your FPS unstable, but it will allow you to see your theoretical maximum FPS. If it's staying over 30 consistently, you know you can add more things or raise your target FPS since you have some extra time each frame. The maximum FPS for the screen is 50, but there's a caveat here, which is that it's only the maximum if you're updating the entire screen. We'll touch a bit more on that later. Another tool that you can use to measure performance is something called the sampler, built into the Playdate simulator. It can be found under View Show Sampler, or for Mac under Window Sampler. If you have your Playdate connected to the computer, you should see in the top left there's a drop down for Device Lua. If you click the sample button, it will start collecting samples from your Playdate, basically periodically asking the Playdate what function it's running at in the moment, and building up a pretty accurate approximation of what functions are taking the most time, because the longer a function runs, the more samples it'll get. Then you can press stop to stop the sample collection. If you sort by samples, you'll see what functions are taking the most time. Then you can use the dropdowns to dig into the call stack to find the offending function. If you're dealing with lag spikes, you can click and drag on the chart at the top to highlight a certain section of your sample. For example, I'll highlight the spike on the graph, and it'll show me what's causing the spike at the top of my sample list. If you instead want to manually measure execution time, you can use the sample function, which takes a label in the form of a string and a function to sample. An easy way to do this is to create an anonymous function for the second argument and wrap it around your code that you want to measure. While your game is running on your Playdate and connected to your computer, it'll print out how long the function is taking to the console. The text is blue if it's coming from your device. If you have white and blue text showing up, the white text is coming from the simulator, so you can pause the simulator to stop those messages. You can have multiple sample calls with different names to test different code paths at once. You can also just manually measure a section of code by calling reset elapsed time at the start of the section of code that you want to measure and get elapsed time at the end. Or call get elapsed time twice and get the difference if you've already called reset elapsed time somewhere else. This gives the number of seconds which pass, so make sure to multiply by 1,000 to get the number of milliseconds. Now that we've looked at how to measure performance, let's look at how to improve it. I've separated possible performance issues into roughly 3 categories: memory, code execution, and drawing. The first category we're going to look at is memory, because I think this probably has the most impact on performance if not handled correctly. To begin, let's talk about what memory even is. When we write code, we usually have some sort of data that we do operations on. For example, a heal function takes a health value and adds some heal amount. The health and amount is the data, and the addition is the operation. Or we have some image we want to draw. The image is the data, and drawing it is the operation. The data has to be stored somewhere, and that's where memory comes in. However, there's a lot of different types of memory, and each type takes a different amount of time to access, which will greatly affect your performance. Let's take a look at the physical Playdate circuit board to get a sense of memory. The parts we're concerned about are this red square, this yellow square, and this orange square. This red square is your CPU, the brains of the Playdate. All the actual operations on data happen here, so the data needs to get here somehow. Inside of the CPU is the first type of memory called registers. Registers are the fastest type of memory to get and store data, but the trade-off is that they are very small. There are 13 general purpose registers that are 32 bits in size each. As a reference, just a single number will take 64 bits, so it's not a lot of memory. However, there's another type of memory in the CPU called the cache, which is a lot bigger that we can use. On the Playdate website, we can see that the total cache size is 8 kilobytes, but it's split into 2 4-kilobyte caches, an instruction cache and a data cache. The part we care about is the data cache, so that's only 4 kilobytes. However, it's still about 160 times the storage capacity of registers. The trade-off is that it's slower to access than registers, but it's still relatively fast to access, so it's very important. This is a trend with memory. The larger the storage capacity, the slower it is to access. The next type of memory is RAM, or random access memory. There's 2 types of RAM on the Playdate. The first one is called Data TCM, or DTCM, where TCM stands for tightly coupled memory because it sits close to the CPU, somewhere inside of this red square. This has 64 kilobytes of space, but we can only use 10 kilobytes of it because the rest is reserved for the system and the screen. There's something called the stack that lives here. The speed to access this is pretty comparable to the cache, but the stack is not something we'll be talking about a lot, so for now, let's just ignore the Data TCM. The second type of RAM holds something called the heap, but you'll usually hear it referred to broadly as just RAM or memory. It sits right outside the CPU in this yellow square, and we can see on the Playdate website this holds 16 megabytes of space. That's about 4,000 times the size of the cache. But because it's outside of the CPU and larger, it's even slower to access. Let's think about an example to really conceptualize this idea of memory. Let's say you're trying to build a Lego set. The data is the Lego bricks, and the operations are putting the pieces together or onto the build. The registers are the pieces that fit into your hand. You can't hold that many pieces, but they're immediately accessible to use. The cache is something like a bin full of pieces that is next to you. You'll have to reach over and rummage around the bin to find the pieces you need, but it's still relatively quick to get. The RAM is like a storage space that you have in your basement. You'll need to go all the way downstairs to get the Legos you need if you don't have them in your hand or the bin next to you, which will be a decent amount slower. Something important to know about the cache is that it's not really its own storage. The purpose is to be a bridge between RAM and the CPU. Let's take a look at a really simplified example of memory to see how this works. On the right-hand side, we have RAM. You can think of RAM as a list of cells, each cell holding some data. Every cell has an address associated with it, the yellow numbers in this diagram. Addresses are in hexadecimal format, so it's prefixed with 0x. And they're sequential, so in this example, since it starts from address 1, it goes 2, 3, 4, and so on. Each address has some data stored in it, which are the white numbers. In code, this might be an array, so it'll look something like this. On the left, we have the CPU. Let's say we're trying to add two numbers together that are in this array, index 1 and index 3, which happen to be stored at address 1 and address 3. First, we'll request the value at address 1 from the cache. However, the cache doesn't have the data since it's empty. We call this a cache miss. In our Lego example, this is like looking for a piece in the bin next to you and it's not there. Therefore, we're forced to make the longer trip to RAM to get our data. To be efficient, we grab whole sequential chunks of data from RAM each time, which is called a cache line, and then copy it into the cache. In our Lego example, if you go to the basement to find a piece, instead of grabbing just a single piece, you grab an entire bin instead, which is the cache line. We then have the data, a value of 10, so it's sent back to the CPU, which is then put into a CPU register. We now need the next value at address 3, so we request that from the cache. However, since we pulled an entire cache line, the value is actually in the cache already. This is called a cache hit, so we can quickly return this value and store it into our register. Then we can actually run the calculation. Let's say we want another value, this time the value at address 5. Again, we ask the cache, however, it's not there, so we get another cache miss. But the cache is full, so we have to first evict the cache to empty it. Then we grab the new cache line. For the sake of example, we thought about the cache like it can only hold one cache line, but the cache can hold a lot of cache lines, as each cache line is 32 bytes, so really you can hold up to 250 different cache lines. And you only have to evict one at a time on each cache miss. As you can see, sequential memory access is important to maximize cache hits, which we'll talk more about later. Getting a cache miss sounds pretty slow, but it's really not the worst thing. It can get a lot slower with our last type of memory called flash storage, which is this orange square over here. On the Playdate website, you can see that flash storage has 4 gigabytes of memory, which is about 250 times the size of your RAM. Not only is it larger, but it's also a special type of memory, which is non-volatile memory. If your Playdate ever fully turns off, everything inside of your RAM, your cache, and your registers will be erased, because it's what we call volatile memory. However, everything in flash storage will remain. This is important since all your games are stored in flash memory, but it means it'll take even longer to get data from it, magnitudes longer. For our Lego example, flash storage is like getting in your car and then driving all the way to the store to buy new Legos and bringing them back home. When we're only working with 1/30th of a second each frame, this is a lot of time. With performance, this is what we would call an expensive operation, because our currency is time and slow things cost a lot. You'll also hear flash storage referred to as the disk, which is a reference to another type of non-volatile memory, hard disk drives, that use a physical spinning disk to store memory that used to be more common. It's kind of like how we still stay rolled down the window. So, getting data from flash storage will often be referred to as loading from disk. When looking at our 4 different types of memory, the registers are pretty difficult to optimize around since they're so small, and it's hard to predict how they'll get used, so let's just ignore the existence of registers. With the cache, you can do a lot of optimizations in C, but it's a lot harder to do in Lua because how Lua manages memory layout is largely abstracted from us. It's still possible to try and lay out your data in a cache-friendly manner and reduce the chances for a cache miss, but we'll come back to it later. Now, what's left is RAM and flash storage, which we have a lot of control over when we access. Our goal is to try to read from RAM as often as possible and to avoid making the long trip to flash storage. The main strategy to do this is by preloading our data from flash into RAM so it can be accessed faster. This process is known as caching data. If you notice, that's the same root word as our cache memory. That's because it's doing the same thing. It's caching data from RAM and making it faster to access. Let's take a look at some code to illustrate how we might cache data. In this example, in the update loop, we're creating a new image and drawing it to the screen. However, let's think about this new image call. We're getting our image data, but all our assets are stored in flash memory. So we're making the long trip to the store to get our image, and we're doing it every single frame. Here, since we're only loading a single 32 by 32 image, the effects are not that noticeable. I've uncapped the refresh rate, and it's running comfortably at 50 FPS. However, let's say we're loading and drawing 10 different images instead, which wouldn't be uncommon in the game. Now we're dropping to around 25 FPS, which is below our target 30 FPS, so we're already lagging. This is because every time we're asking for the image data, it's making the long trip to flash storage and back, and we're doing it 10 times. The time it takes to load assets is also proportional to the size of the asset. For example, let's say we're loading this 400 by 240 background image instead 10 times. It drops down to 13 FPS instead. Of course, you probably wouldn't be loading 10 different backgrounds at once, but if you have an image table and you're loading a sprite sheet, those can get pretty big, depending on how many frames the animation has. What's the solution? It's inevitable that we're going to need to go to flash storage to get the data at least once. However, since it's really the same data each time, why can't we just get the data, then save it so we only need to go a single time? An easy way to do this is just to move our new image call outside of the update loop. Anything called outside of the update loop will run a single time when the game starts. What we're doing is getting our image data from disk and keeping it in our RAM, and every time we're accessing that variable, we're getting it from RAM instead of flash storage. Now we're back to comfortably drawing our 10 images at 50 FPS. We can do this with all different kinds of assets. That includes fonts, music, and sound effects. Sound effects are a particularly important one to consider caching, as they usually play in response to user input. If the player gets a lag spike every time they press A to jump because you're loading the sound effect from disk each time, it might be easier to notice. Caching is great, but it's not an entirely free solution. There is a small cost that we're incurring. The first is that we're increasing our game load time. That's the time it takes when we launch our game from the Playdate launcher until our game actually starts running. I would say in most cases, it's probably worth it to increase the load times a bit so that we can have a smooth play experience. However, there's a rare case when you're loading too many assets where you run into an issue. The Playdate has a built-in watchdog timer that checks to see if your game is stalling for more than 10 seconds. If so, the Playdate will force your game to crash as a fallback because it's assuming that your game got stuck in a bad state. So if you're preloading a lot of assets, or assets that are large in size, then your game will fail to launch. No problem, we'll just make sure that it stays under 10 seconds, but there's an additional consideration that you have to make. While your game might take less than 10 seconds to load on your Playdate, it might take more than 10 seconds on another device. That's weird because each Playdate has the same hardware, but this is because the speed of flash storage actually slows down based on how full it is. If your game takes 9.5 seconds to load on your device, if someone else's Playdate is full of games and has 3.9 gigabytes of their 4 gigabytes used up, it might push the load time over 10 seconds. So you'll want to have a bit of buffer in your load time. Okay, now we've made sure that our load time is under 10 seconds, but we still have some assets that we want to cache. What do we do in that case? One thing to try is to simply decrease the size of your assets. There's not much you can do with images, but with audio, there's some things you can do. One thing is to export your audio in a compressed audio format. The ADPCM format is the recommended compressed audio format for the Playdate. Another thing you can do with audio is to mix your audio down from stereo to mono, which will halve your file size at the cost of losing stereo sound. If you're using Audacity, if you see two tracks like this, the audio is in stereo. You can then go to Tracks, Mix down to mono. Then you can go to File, Export as WAV, and then choose IMA ADPCM as your encoding. Another possible strategy is to load some things only when you need them. For example, loading all the images used in a scene the first time you load into a scene. However, this will cause a random hiccup in your game that might be jarring for the player. You can smooth things out by creating some sort of loading screen. Let's take a look at how we might create that. First, we'll create a table with the paths of all the assets we want to load. In this example, I'll just use images. Then we'll create another empty table that will hold all the loaded images. We'll also create a variable to keep track of how many images we loaded so far. In our update loop, we'll check if our loaded image count is less than the number of paths we need to load. If so, we can increase our loaded image count by 1 and use that as an index into our image path array to get the next path to load. We'll load the image and then store it into our images table with the path as a key. We can then calculate what percent we're at in the loading process, and using that, we'll draw the actual progress bar. We can draw a rectangle as the border with draw rect, and then use fill rect to draw the fill within the same dimensions. However, we'll multiply the width by the percentage amount. If we've loaded all of our images, then we can run our game code instead. In this example, I'll just use one of our images that we've loaded, which I can access with the image path in the loaded images table. And then we'll draw that image. If we run it, it'll look something like this. Now, in the documentation, there's an example that uses coroutine yield instead to load all our assets in a single loop. If we want to do it that way instead, we can swap the loaded image count with a boolean to know if we've loaded all our images yet. Then, in our update loop, we'll check if we haven't loaded all the images and then loop through all our image paths at once. We'll do the same steps as before, but use our loop index to get our image path. After the loop, we'll set our images loaded boolean to true. Afterwards, we can run our game code using our loaded assets. If we try running this now, what will happen is the game will freeze from all the assets loading at once, and then you'll see a filled loading bar for a single frame. The reason is that the screen doesn't update until after the update loop. So this entire loading loop has to finish before we're able to update the screen. However, there's a way to allow the screen to update while we're still in the middle of the update function. The update function is running as something special called a coroutine. We can use the coroutine yield call to yield our execution temporarily to allow the screen to update. Then, once it's done drawing to the screen, it will come right back to the place that you called coroutine yield. If we put this yield call at the end of the loading loop, what will happen is that every time we draw the progress, we'll reflect the drawing to the screen. If you're using sprites to draw instead, you'll need to put a sprite update call before the coroutine yield so that the sprites can be updated before the screen is drawn. If you run this, it'll function exactly the same as what we had before, but just written in a slightly different way. Okay, back to the trade-offs of preloading data. The first one was load time. The second trade-off is you're basically trading memory for speed, and your memory budget isn't infinite. We only have 16 megabytes of RAM to store all these loaded assets. If you run out of RAM, your game will crash. However, while 16 megabytes doesn't sound like a lot, for Playdate games, that's actually a pretty good amount. The reason is that images are extremely small. A normal color PNG needs to keep track of the color of each pixel. However, Playdate images only need to keep track of black or white, so it's only 1 bit per pixel. This 400 by 240 pixel background is only about 2 kilobytes, while this full color version is about 145 kilobytes. The issue really comes with audio. This short sound effect is about 36 kilobytes already. And this piece of background music is about 2.5 megabytes, which by itself is already 15% of our memory budget. Luckily, with music, it's usually pretty manageable because there's a way to balance performance with memory. Instead of loading the music into your memory all at once, if you use a file player instead of a sample player, it will stream the audio file from disk, which means it will load and unload the audio file bit by bit as it plays from flash storage, which takes less memory but with a trade-off of a greater performance cost. In any case, these are all things to consider when thinking about caching data for performance. My recommendation is to preload and cache everything and only start worrying about it if you run into issues. I haven't had to worry about running out of memory or timing out the watchdog timer in any of my games so far. You can see how much memory you're using by first selecting Playdate, malloc pool, 16 megabytes, and then view show malloc log. The malloc log for Mac is under Window, malloc log. In the bottom right or the top left for Mac, under heap used, it'll show how much memory you're using. If you're legitimately running out of memory, then you'll need some way to clear it out before you can load anything else. Let's say you load in a giant audio file. How do we clear it from RAM? Lua has an automatic system called the garbage collector, commonly abbreviated as GC, that clears out memory if it's not being used anymore. It does this by checking if the data loaded into memory is accessible, and if it's not, it will clear it from memory. Here's a simple example. Let's say when we press the A button, we load a sound effect and store it into this variable and then play it. However, this variable is local, so it will go out of scope at the end of our conditional block. There's no longer anything that's pointing to the sound effect data that we've loaded. Therefore, it's marked as garbage and eventually cleared. Now, if we instead cache the sound effect at the top of our file, this variable will never go out of scope. So there will always be a reference, meaning it will never be marked as garbage. In this case, you can manually remove the reference by setting the variable to nil. Then, eventually, the garbage collector will get around to clearing it out from RAM. However, let's say we create a sound effects table and add the sound effect to the table. Even if we set the original reference to nil, there's still an existing reference inside of the table. We'll need to either remove the entry, set the entry to nil, or set the entire table to nil in order to remove the remaining reference so that the garbage collector can get to it. You must remove every existing reference to an object in order for it to be garbage collected. What's more is that the garbage collector itself is something you have to worry about for performance, because if you're producing a lot of garbage, then the garbage collector can take a considerable amount of time to crawl through all the objects and clean them up. This will usually show up in the form of random lag spikes that don't seem to be caused by anything you're doing. What's important to note is that the garbage collector performance depends more on the amount of objects rather than the size of the individual objects. So usually, assets aren't the issue. It's the smaller things that get created more frequently in memory. Assets are not the only things that get loaded into RAM. When we create new things in code, which we'll broadly refer to as objects, it allocates some space in memory for it to exist. The objects we care about for this fall into 3 categories: tables, functions, and strings. Whenever you create a table, it actually takes a bit of time to make. This is because we're making the trip to RAM and allocating some space there for it to occupy. This includes all SDK objects like sprites, timers, geometry, vectors, anything you create with new, because those are all technically tables. Functions are a kind of object too. Usually this isn't an issue because it's unlikely you're creating a bunch of functions constantly and then throwing them away. The one case where that might be common, however, is with anonymous functions. Strings are also a kind of object as well. Every time you make a new string, it has to store it in memory. However, strings are a little bit special because when you create a new string, Lua will cache it automatically, so if you make the same string, it will reuse the save string object. It's only when you're making new, unique strings that it creates a new object. If you're creating a lot of objects, it's not necessarily a big deal, but it becomes more of a problem when the object gets created temporarily and thrown away after. Then the garbage collector has to do a lot of work, which can kill your performance. Compared to loading assets, creating a single table and then having the garbage collector clean it up is pretty much nothing. But it can add up a lot in hot paths. For example, if you're creating a single table, for my measurements, it takes something like 0.05 milliseconds, which is about 0.15% of your frame time, which is pretty much nothing. But doing it 100 times in a loop will take around 15% of your frame time, which can be a huge deal. On top of that, if you're not reusing the tables, those need to be garbage collected, which adds additional time. Let's talk a little bit more about this concept of frame time. We can think about how impactful code is by thinking of our available frame time, which is how much time you have each frame to run your code. At 30 FPS, that's 1/30th of a second, or about 33 milliseconds. If your code and drawing together takes less than or equal to 33 milliseconds, or 100% of your frame time, then you'll still be running at 30 FPS. But the moment you go over 100%, your game will start slowing down. 3 milliseconds might not sound like a lot, but if you think about it as 10% of our available frame time, it puts it into perspective a bit more. If we're maxing out our frame time, an extra 3 milliseconds will drop our frame from 30 FPS down to around 27 FPS. Or inversely, if your game is running at 27 FPS, all you need to do is save about 3 milliseconds of time each frame to get back to 30 FPS. Back to our object creation code. How would we address this if it's a problem? First step is to take a look at hot paths. Look in your loops to see if you're creating tables or objects, and assess if you really need to create a table or if you can store the individual elements into separate variables. A common case where tables can be created unnecessarily are with the built-in geometry types. If you're keeping track of a position, you might think it's convenient to create and use the point or vector object. Really, you're creating a new table in memory and then likely throwing it away immediately afterwards, taking extra time to make the object and then garbage collecting it. If you do it a lot, it can add up. Simply splitting the x and y values into two separate variables can greatly improve your performance. If you're returning a point from a function, you can instead use multi-return to return multiple values, instead of creating a new table and returning that. If you want to use an object because it's convenient or required, you can consider creating the object once and then reusing it. For example, we want to use the built-in Vector2D magnitude method. We can create a new Vector2D object each time to call the method, or we can just create the Vector2D object once and then reuse it by overriding its properties, which can be a lot faster than creating and destroying an object each time. If you need multiple objects, you can consider creating an object pool. For example, if you're creating a lot of sprites in a loop, maybe you can create a list of sprites once, and then grab one from the list to use and put it back once you're done using it. You're essentially caching the objects in memory, so you never have to pay the cost of garbage collecting the object and only have to spend time to create it once. This can start to add up if you've extended sprites into a subclass and your init method has a lot of code in it. As the cost of creating new objects increases, the more impact it will have to create a pool of objects to reuse. Similar things can be done if you're creating a lot of anonymous functions. If the functions are all the same, create the function once, and then reuse the same function instead of creating a new anonymous one each time. But if it's not happening often, then I usually just use anonymous functions to make it cleaner, and usually functions are not very large objects. For strings, I wouldn't worry about it too much because of the built-in optimization. However, it can potentially cause issues if you're frequently concatenating them to create new strings. If you find yourself using the concat operator to combine a lot of different strings at once, each concat call creates a new string that then becomes garbage to be collected. In the case that you're measuring that it's taking a long time, you can try calling table.concat instead, which takes an array of strings and combines them into one string and only allocates one new string. As a bit of an advanced technique, you can actually mess with the settings of the garbage collector. For example, you can pause the garbage collector and then manually collect garbage so that you can choose to run it when there's some downtime. The docs say that you can call this setCollectGarbage function to pause it, but I did see a report that it's potentially bugged, so you can try calling collectGarbageStop instead. You can manually collect garbage with collectGarbageCollect or just collect garbage. You can adjust how long the garbage collector runs for with set minimum GC time and set GC scaling. And you can call collectGarbageCount to show how much total memory is being used to help debug memory issues. Okay, we've covered everything about memory, but loading things from memory and the garbage collector are not the only things that take time. Every line of code takes a little bit of time to execute. However, not all code is made equal. There are some operations that can take longer than other ones. The main culprits are any functions, mainly SDK functions, because there can be a lot of code hidden behind the function that has to be executed. For example, let's say we call the all overlapping sprites function from the SDK. Think about what that's doing. It has to loop over all the sprites with the collision box, check to see if there's an overlap, taking into account collision groups and masks, and then it has to allocate a new table to store all the overlapping sprites to return to you. That sounds like it can get pretty expensive. The sprite positions aren't changing within a frame, so if you're calling it multiple times in a single frame, you could be doing a lot of extra work. Back to our caching strategy. Just save the result of the function, and you can use the saved result instead of calling the function multiple times. Another thing to consider is how the function is implemented. Most SDK functions are implemented in C, which will generally be pretty fast, but there's some that are implemented directly in Lua, which is a lot slower than C. It's not documented directly in the SDK documentation, but if you go to where your Playdate SDK was installed, in the core libs folder, you can find all the implementations of the functions that are written in Lua. To check if a function is implemented in Lua, you can just do a code search in the folder for the name of the function. Most core libs Lua functions aren't written with performance as the main priority, so it's likely you can write your own that's faster. A sort of notoriously slow set of functions are the image with text and sprite with text functions. If you check the implementation, it's calling this beefy layout text and rect function that calculates text layout, which does a lot of things. The function is designed to be very general and handle a broad set of cases, which is fine for most cases, but in situations where performance is priority, you can probably cut out most of the functionality. For example, if the text is only on a single line, here's a basic version of that function that's just 5 lines of code. If you do need the more complex image with text function, maybe call it once and then cache the result, and then reuse that instead of having to call the function each time. You can also split up the work of expensive functions over multiple frames. For example, collision checking is an expensive operation. However, checking collisions every other frame will basically give the same results for most cases. So you can check the collisions for half of the entities on one frame and half on the other, having the collision checking work you have to do each frame. Another thing to consider is that calling a function in itself has a bit of overhead. In this example, we're doing nothing, just calling the function, which is empty. If we run this 100 times, it takes about 0.33 milliseconds, while the inline version without anything takes about 0.07 milliseconds, which is the work to run the loop. It doesn't sound like a lot, but each frame is about 33 milliseconds, so the work to run a function 100 times is about 1% of the frame time. If you're looping over a list of 100 elements and calling 5 different functions, that adds up to 5% of your frame time, which can be pretty significant. With this, we're getting into micro optimizations here, so I wouldn't go around killing your project's code readability by inlining all your functions, but if you're trying to squeeze out some performance gains on a hypercritical hot path, it's worth considering if you should inline your code. Another commonly used function that you have to be careful with is the print function. The print function, when called often, can be pretty slow, so when you're packaging up your game for release, make sure to remove any print statements and hot paths that you use for debugging, so you're not slowing your game down for no reason. If you're not having any performance issues, I wouldn't worry too much about these things, but if your game starts to lag, I would look at hot paths and loops and then comb through the functions being called. Is there anything that can potentially be a slow function? Is it something that you can pre-compute, call a single time, or split up? Use the sampler to help find any expensive functions. Something else that isn't entirely intuitive is that table lookups take time as well. When you look something up in a table, it has to take a key and run it through a special function called a hash function to find where the data is in the table, which takes time. The table also exists somewhere in RAM, so you'll need to go and get it as well. You can generally check if something lives in memory by printing it. When I print a table reference, it gives me a number. This number is in hexadecimal format and represents the address that the object lives in memory. The cost is multiplied with each successive nested access into a table. For example, a common one would be with SDK functions. When you call playdate.graphics.sprite.new, it's doing 3 table lookups, one for each dot. If you're calling this often in a loop, then it might be worth caching the function reference into a variable, like new sprite, and using it directly. Or if you're getting data from a table, just caching it into a variable and using that instead. It's not a huge difference. From my testing, it's similar to the function call overhead, so I wouldn't go around localizing every single table call, but in high impact hot paths, it might be worth trying. There are some things that might not seem obvious are table accesses, but they are. One hidden one is global variables. Whenever you use a global variable, you're actually accessing a giant invisible table, _env, which you'll also see referred to as _g. They're slightly different, but for our purposes, they point to the same table. For example, calling this myGlobalVariable is really just syntactic sugar for _env.myglobal. Since we're doing a table access, it takes a bit of time, so while it looks a bit silly, localizing a global variable like this makes accessing it slightly faster. The SDK Playdate variable is a global variable as well, which is why it's recommended to localize the Playdate variable at the top of every file. There's a lot of Lua performance advice out there, and one of the most common ones is to localize everything. This is because of the table access that we talked about, but also local variables are stored on a special region of memory called the stack. that's usually faster to access. In most other systems, the stack lives in RAM next to the heap outside of the CPU. But for the Playdate specifically, the stack is stored in the data TCM inside of the CPU, so it's even faster to access. This sounds great, localizing things definitely helps, and they're pretty easy changes to make so it doesn't hurt, but individually it's not a huge difference, so I wouldn't be too obsessive about it unless you're in a hot path. Another area where table access is common is with the Playdate SDK's implementation of classes. Let's say you have a sprite called player. When you call player move to XY, the colon is just syntactic sugar. It's calling player.moveTo player XY. Because of how classes use metatables, all methods point to the same function, so you can either cache the method reference from the class itself or from the class instance. Then you can call the method like so. Personally, it's such a small optimization and it messes with the readability, so I wouldn't do this in most cases, but it's there if you want it. However, table access can add up pretty significantly within the class methods, in the case that you're creating your own class and writing your own methods. In class methods, you're accessing properties using the self keyword, but notice that we're doing a table access on the class instance each time we're doing this. It's unavoidable when using object-oriented programming, but really OOP and classes in Lua are not very conducive to performance. So in performance-critical scenarios, it might be better to replace it entirely with a data-oriented design, which we'll briefly touch on later. However, classes are very convenient, so if you're not hurting for performance, I wouldn't go ripping out all your classes. One random performance tip about classes is that the ISA method to check for whether a class is of a specific type can potentially get slow, especially if you use a lot of inheritance. If you look at how it's implemented in core libs, under object.lua, you can see that it's looping through all of the parent classes. An alternative option is to just set a property manually, like type, to check for the type instead. If you're extending from the sprite class, you can use setTag and getTag as well. When you have a table, a common operation is to loop over it. However, there can be a big difference in performance just from how you write the loop. A common way is to use a generic for loop, using the pairs or iPairs iterator. Looping over this array of 100 elements, the pairs iterator took about 1.3 milliseconds, which is about 4% of your frame time at 30 FPS. It's said that iPairs is faster, but from my testing, it's about the same. However, since we know that the keys are sequential numbers starting from 1, we can just use a basic numeric for loop. This took about 0.15 milliseconds, which is about 0.5% of your frame time, 8 times faster. That's a big discrepancy from just simply changing your loop type. This is because while pairs and iPairs are slightly easier to work with, they're doing additional work to provide that interface, which scales with the number of elements you're iterating over. When you're working with hash tables with string keys, however, we're sort of stuck with using the pairs generic for loop since we need to find all the keys of the table. You can save a little bit of time by storing the keys into a separate array, and then using a numeric for loop to loop through the keys array, and then use that key on the hash table. This generic pairs for loop over 100 elements takes about 1.3 milliseconds, while the other way takes about 1 millisecond, which saves about 1% of your frame time. Saving time from doing nothing except changing the loop type is a nice and free optimization to make, and if your hash table can be reorganized into an array so you can take advantage of the faster loop, it might be worth thinking about in performance critical scenarios, but since the difference is pretty small, it probably won't matter for most situations. Another thing to think about is alternative ways to structure your data in arrays. Let's say we want to store a list of positions, maybe like the positions of all the enemies on screen. One way would be to store the position as an object with an x and y element. However, another way might be to store the x and y values into separate arrays. If we store the position into objects, we're going to have to do extra hash table lookups, and the objects will be spread out more in memory, lowering our cache efficiency. If we store the value directly into arrays, we're only doing array lookups, and the data is packed together in memory so we can fill up our cache more efficiently. From testing, this leads to around a 1 millisecond faster loop over 100 elements, which is about 3% of your frame time. With more properties, it can add up even more, so it could be something worth considering for performance. Of course, we're not just looping over arrays. Frequently, you'll have to create arrays and modify them by adding or removing elements. There's a few ways to make this process faster as well. Let's say we're creating an array of 100 elements. What we can do is use the table.insert function, which adds an element to the end of the array. When caching the insert function reference, it takes about 2 milliseconds. However, the table insert function has some overhead associated with it, so we can do a little better by just using the length operator and adding 1 to it, which accomplishes the same thing. This takes about 1.3 milliseconds instead. However, the length operator is technically a sort of function as well, so in this loop, since we already know the index we're on, we can use it directly, which takes about 1 millisecond instead. But we can go even further. How tables work is that when we add a new element, Lua needs to allocate additional space in memory for each new element, which takes time. This process will happen on every individual element inserted, which can add up. In this case, we already know how much space we need, space for 100 elements. So we can use a special table.create function, which can pre-allocate space for the table all at once. This function takes two arguments. The first one is for how many elements you want in the array part, and the second argument is for how many elements you want in the hash part. For this table, we're only using the array part, so we can do table.create 100, 0. Now it only takes about 0.3 milliseconds instead. Not bad. We went from 6% of our frame time at 2 milliseconds down to 1%. For table.create, even if you don't know the exact number of elements you have in your table, just an approximation is fine. If it's a little underestimated, you're still saving the work of allocating memory for most of the elements, and if it's a little over, you've only wasted a little bit of memory. Removing elements from arrays is another slow operation. This is because every time you remove an element, it has to shift all the following elements that come after it to fill in the gap. A trick you can do is to overwrite the index you want to remove with the last value of the array, and then set the last element to nil, which cuts off the end of the array. This messes up the order of the array, so you can only do this if you don't care about that, but it ends up being a decent amount faster on average if you're removing elements often. Lastly, for this code execution section, I wanted to talk about const. There's a const attribute that marks a variable as something that cannot be reassigned, and it's sometimes said that it will improve the performance of accessing that variable slightly. From my experience in testing, it has either no or negligible amount of impact, so I would just use it if you want the variable to be a constant and not for any performance reasons. The last topic we'll cover is drawing, because drawing to the screen is slow and can significantly impact performance. The most straightforward way to draw to the screen is just by directly drawing it with draw functions. In this example, I'm drawing a bunch of images to the screen. I've set the refresh rate to 0 so that the FPS is unbound, and we can see the maximum FPS. The higher our FPS, the faster our code and drawing is running. First thing that you'll notice is that the FPS counter is hovering around 60 frames per second. That's weird. Isn't the maximum FPS 50 according to the documentation? Well, there's a caveat to that. That's if we're updating the entire screen. That's because in the time it takes to update the entire screen, we can't do it more than 50 times a second. So we're bound by the screen hardware. However, if we're only updating part of the screen, it takes less time. So we can either update the screen more often or run more code per frame. If we highlight screen updates, we'll see that it's not updating the entire screen, only the regions we're drawing to. Specifically, it's the number of rows we're updating. If we're drawing one column of images, but it's the same number of rows as before, then it has around the same FPS. However, if we draw a section that only covers some of the rows, then we're drawing at around 300 FPS. The FPS counter caps out at 99. This is good to know. If we update less of the screen, drawing takes less time and we have more time per frame to run our own code, giving us more performance bandwidth. However, we're not just drawing static images all the time. Things change and move on the screen. Once things start to move, we'll get smearing. So usually you'll need to clear the screen between frames. Clearing the screen updates the entire screen, so we're back to our 50 FPS limit. This is where sprites come in. You've probably heard that sprites are good for performance, and that's generally true with some caveats that we'll cover later. The reason why sprites are good for performance is that they keep track of whether or not the image has changed. If not, they won't update the screen. Let's take a look at our full screen draw example from before, but draw it with sprites instead. When we highlight screen updates, since nothing is changing, we're not updating the screen. On device, the counter shows 99, but it's running at almost 400 FPS because we're spending pretty much nothing on drawing. This is great because we have more time to spend on running our game logic. However, everything changes when we start moving the sprites. When we wiggle around the sprites, it's only running at 40 FPS. However, when we do the same thing with drawing directly, we're getting around the full 50 FPS. Why is that? The main performance benefit sprites have is not drawing to the screen or only drawing part of the screen. However, if your sprites cover the whole screen and are constantly moving, it's always updating the entire screen, so really it's no different from just drawing directly, but with the added overhead of all the work to keep track of the sprite's dirty recs. There's a flag that you can set always redraw, that you can use to disable dirty rec tracking. However, this only brings it up to around 42 FPS. What else is causing the slowdown? Well, remember all the stuff we covered with the table access and the cache? When looping over all the sprites, we're calling the move by function on all the sprites. Not only is there a function overhead, and not only is there table access overhead, but each move by call is accessing the position data from each sprite, and each sprite can be in completely different regions of memory, potentially trashing our cache. When we're drawing all the images directly, it's a simple loop, and we're not accessing different regions of memory. Let's take a look at a more concrete example. Let's say we wanted to add a bunch of projectiles to our game. These projectiles will move in all different directions and across the whole screen. How I would probably approach this with sprites is by extending the sprite class and creating a projectile class, and then initializing it with some x velocity and y velocity properties. Then we'll extend the update method to move the projectile by its x and y velocity. We'll add a bit of extra code to just loop the projectile around when it hits the end of the screen, and we'll create 100 of these sprites. However, when we run this, it's a complete disaster. It only runs at around 12 FPS. But most of this is actually because of all the dirty rect tracking that the sprites are doing. If we set always redraw to true, we're back to around 40 FPS. However, it's possible to do a little better. Instead of having separate objects that hold properties that can be scattered all around memory, let's have 4 separate arrays that keep track of the x and y positions, as well as the x and y velocities. When we quote-unquote create the projectiles, we're really just adding data to a list instead of creating a new object. This is something more akin to data-oriented programming rather than object-oriented programming with sprites. Here we already see an immediate benefit. Creating 100 of the sprite objects takes about 90 milliseconds, which is almost 3 entire frames, so your game will experience a lag spike. But initializing the arrays only takes about 5 milliseconds, which is about 15% of a single frame, a whole 18 times faster. Not only that, but when you destroy a sprite object, it will need to be garbage collected, costing additional time, which you don't have to worry about on the data-oriented side. Of course, with sprite objects, you can create a static pool of sprites that get reused to resolve that issue, so potentially a non-issue on the garbage collection end. In our update loop, we'll first clear the screen and then loop through all the projectile data arrays. For the length, you can just use any array since they all have the same length. The type of programming is a bit different from object-oriented. We'll need to manually get the properties from arrays, which we'll reference by index instead of object reference. I'll get the x, y, x velocity, and y velocity values. Then, we'll need to manually update our position, so we'll add our velocities to our position and store them in a new variable. Like our sprite example, we'll loop the position if it hits the end of the screen. And importantly, we'll need to store our new position back into our arrays to make sure the data gets updated. Lastly, we'll draw our image directly at the new position. If we run this, we're easily hitting 50 FPS, our max full screen refresh rate. There's a lot of factors at play here from what we've learned so far, from the additional overhead from the sprite system, which is related to what we learned about with expensive functions, to the sprite objects being stored in different places in memory, and the arrays being packed together, which is related to what we learned about memory and the cache, and the sprite updates doing a lot of hash table access, while we're only doing array access on the data-oriented side, which is related to what we learned about how tables work under the hood. The more things you add, the more you can take advantage of the data-oriented design. For example, using the built-in sprite collisions is convenient, but you might find that writing your own collision might be faster. When I made my games Core Fault and Propeller Rat, that's what I found. Propeller Rat specifically runs comfortably at 30 FPS connected to Mirror, with projectiles and collisions flying around the screen, and it's all written in Lua. All the source code for my games are open source under the MIT license on GitHub, so feel free to take a look. I'll leave a link in the description. There is a limitation with our current implementation, where if we're only drawing through some of the rows, we're still locked at 50 FPS because our clear call is clearing the entire screen. However, we can actually mix sprites and drawing together to get the best of both worlds. If we replace our clear call with a sprite update call, the sprite system will take care of the background and we'll be drawing on top of all our sprites. You can see now that we're only doing screen updates for the parts that we're drawing to, and if we run this on device, we're hitting around 75 FPS. Again, this is really more of an exception that drawing directly is faster than sprites because it's something we're constantly moving. It's covering the screen and there's a lot of them, so the dirty rect has to be recalculated constantly over many sprites. For most cases, sprites will be faster, but this data-oriented approach is a good tool to have in your toolbox for certain cases. In the Playdate SDK, there are a bunch of draw functions to draw different primitive shapes, like draw a circle at point or draw a triangle. However, generally, if you have an image object, like if you just have a PNG of a circle or triangle and load it into an image, it will be faster to draw that than to draw the primitive shapes because the shape drawing needs to do some extra math to calculate where to draw the pixels. With simple draw calls, this isn't a big difference, but when you have more complex drawing, it starts to add up. But sometimes it's unavoidable or easier to use the primitive drawing methods, like when you have dynamic drawing that changes with the state of the game. Let's take a look at what we can do in that situation. In this example, we're manually drawing this little Playdate sprite with a bunch of individual primitive draw calls. When we draw a bunch of these to the screen, it drops down to 16 FPS. To fix this, we can cache the result of our draw calls. We can do this by creating an empty image, and then use push context on our image and draw into it a single time. We've effectively stored the result of all our draw calls into the image, which we can then draw instead. Doing this brings us back to 50 FPS. Text is also another draw call that can take some time. This is a good candidate for pre-rendering into an image and using that instead. Another common use case for drawing primitives is to draw particle effects. You can pre-draw particle effects into images, or you can use an external tool to generate a sprite sheet for particles. For example, I have this fire particle effect. This would be very difficult to render in real time on the Playdate. However, it's actually just images from a big sprite sheet. I created and generated this from an external tool called Sprites, which is a paid tool that allows you to make particle effects and export them as a PNG. Another similar paid tool I've used is Pixel Over, which allows you to do something similar. However, if you're looking for a free alternative, another Playdate dev, Tomas Franco, who made Deep Space Dapper Squad, made Particle Sizzler that is designed for the Playdate. Other options are making your own particle rendering pipeline with other tools like Blender or Godot. Another drawing operation that can get expensive is rotating or scaling an image. This is mainly because there's no GPU on the Playdate, so it all has to be done on the CPU. It all depends on the size of the image. The larger the image, the slower it is. When you're rotating or scaling large images, or doing a lot of it, then it can start to get pretty slow. In this case, you can cache the images into an array. For example, you can loop from 0 to 359, and store the rotated images in a loop. This sort of takes a while if you do it all at once, so you can do a lazy loaded version that checks a cache whenever you need a rotation to see if a rotation has been saved. If it has, then use that one, and if not, then you can rotate it at that moment and then store it for future use. Another thing you can do is to pre-bake all the rotations and scales beforehand. You can actually write a Playdate application to do this for you, with the playdate.datastore.writeImage function, which allows you to export a Playdate image as a file. However, there are some external tools that can do that as well. One is called SpriteRote by Samzy, a command line tool that generates sprite sheets for rotations. Another is CleanEdge by Torquedo, which does scaling as well, though this only allows you to export one image at a time. If you create 360 rotations, and the first image is a rotation of 0 degrees, and it increases by 1 degree sequentially, you can directly translate from your rotation degree to the image from the image table by just indexing by the degree plus 1. It's usually not a big deal to have these giant sprite sheets because images are small, but you can make the sprite sheet smaller by only having images for every few degrees instead. Though I'd make it some divisible multiple of 360 to make calculating the index easy. Another optimization you can do is only saving a fraction of the rotation if the pattern repeats. For example, the spinner obstacle I have in my game only needs to have a sprite sheet with 90 degrees because it's symmetrical. Another set of expensive drawing functions are draw blurred and draw faded. As always, we can cache the resulting images, but for draw faded specifically, we can do another optimization in some situations. Here, I'm drawing this image faded at 50%. However, if you notice, it's just a checkered dithering pattern. What we can do instead is mimic the same effect with an image mask. We'll first get the mask of the image, and then use push context to draw into it. We can draw a checkered pattern using the setPattern function. To get the pattern, I'm using this convenient website, GFXP, made by Ivan Sergeev. If we select the checkerboard pattern, click on Playdate Short, and then Add Mask, we can copy this to get our draw pattern. Then we'll just draw a filled rect with the pattern over the mask. The result is the same exact image. The draw faded call takes about 9 milliseconds, but the masked version only takes about 1 millisecond. Before we wrap up, I'd like to make some closing notes. The first one is about different existing hardware versions. Because of previous supply chain issues, there are two different processors used for Playdates. There are older Revision A or Rev A Playdates and newer Rev B Playdates. Rev B has a larger data cache at 16 kilobytes instead of 4 kilobytes. However, it takes a little longer for the cache to get data from RAM, so cache misses are more expensive. The differences means that there are sometimes performance discrepancies between versions, and in some rare cases, they can be pretty significant. Usually, Rev A will run slower than Rev B, so it's possible you might need to factor that in for performance. You can check what revision you have with this online tool made by Paul Straw, or this Rev Checker app made by Ray and ScratchMiner, which I'll leave links for in the description. I wouldn't worry too much about it, but it's something to keep in mind if you're getting performance complaints you're not seeing on your device. They might have a different revision. If you want to dig into the hardware differences for both processors, I'll leave a link to the datasheets for both of them in the description as well. The second note I wanted to make is about when to make performance changes. As you've seen, a lot of these performance improvements require you to forego convenient abstractions and implement things on your own. Other changes impact code readability. Some changes even require substantial rewrites. All of them take some amount of time investment to do. Because of these costs, it's important to contemplate whether any of these changes are even necessary. As indie developers, time is a precious resource. Does your game even have any performance issues? Are you prematurely optimizing because it feels like the right thing to do? It's easy to want to comb over your entire code base, changing everything to be more optimized. If the performance improvement is not very large, it might be better not to do it at all just to make your code easier to understand. If you're getting performance drops or lag spikes, is it even impactful in your game? For example, in low action, turn-based games, players might not even notice a small lag spike if it's not on their turn. Find where the bottlenecks are with the sampler and look at areas of code that get called often. Look at places like your update function and in loops. Optimizing a function in your Playdate update loop that gets called every frame is likely to have more of a performance impact than a function that only gets called a single time on a game over screen. Optimizing code that gets called when you loop over a list of 100 enemies every frame is likely more impactful than code that just runs once. To summarize, optimize performance when you're running into issues to avoid premature optimization, and focus on impactful areas of your code to preserve code quality and reduce wasted effort. And in all cases, measure it. A lot of performance has to do with memory, and how that works is heavily abstracted, so your assumption of what might be an improvement can either prove inconsequential or worse, detrimental. Anyways, that's all for today. If you have any questions, feel free to leave a comment or drop a message in my Discord server. If you found this helpful in any way, these take a lot of work to make, so if you want to support the channel, subscribing helps a bunch. And if you're feeling extra generous, I don't take any sponsors, so the channel is supported by my patrons over at Patreon. Thanks, and see you next time.